welcome to our WJE webinar. My name is Liz Pimper and I'll be your moderator. Our topic today is evaluating the seismic safety of buildings. Do you know if the buildings under your management are adequately safeguarded against a seismic event? How can you tell? During the next hour, we intend to provide you with more insight into seismic safety as it applies to existing buildings. We will discuss what seismic safety means, how building types are used to identify common seismic vulnerabilities, what methodologies are available to evaluate existing buildings, what factors trigger the need for evaluation, and what to consider when planning for retrofits. Our guides for today will be two of the nation's foremost seismic experts from WJE's San Francisco office, Associate Principals Brian Kehoe and Kelly Cobeen. Now let's get started. Brian?
All right, thank you, Liz. Welcome to today's webinar. In the next 50 minutes or so, we're going to be providing you with a brief overview of some useful information regarding the seismic evaluation of existing buildings. So here's an outline of the presentation. First, we're going to talk about what seismic safety means, and we're going to do this in the context of defining what seismic hazards are and defining seismic performance. And then Kelly's going to talk to you about characterizing buildings and common vulnerabilities. And then I'll talk again about evaluating existing buildings, methodologies, and implementation of those methodologies. But first, let's talk about a common misconception. Earthquake-proof buildings don't exist, despite what you might see or read in the media. Instead, what we have is an expectation by engineers that's represented in the building code that damage will occur when buildings experience a design-level earthquake. And what I have in blue is a section of the commentary for ASCE 710, which is the code for minimum design loads for buildings. And here it says, structures designed in accordance with this standard are likely to have a low probability of collapse, but may suffer serious structural damage if subjected to the maximum considered earthquake or stronger ground motion. So two important points in this sentence are, one is that there is a low probability of collapse even for well-designed structures. Because of the uncertainties involved, there is a chance of buildings collapsing even if they are properly designed. And the second is that buildings designed in accordance with the codes may suffer serious structural damage when subjected to design-level ground motions. So there has been an expectation of damage occurring to well-designed buildings when subjected to large earthquakes. So when we're talking about earthquake forces, we need to consider both horizontal motions and vertical motions that might be subjected to the building during an earthquake. Now, for structural design purposes, we consider that the horizontal motions are the most significant in terms of design, and there's two reasons for that. The first reason is that vertical motions are usually less than a horizontal motion in an earthquake. And second, structures are always designed to support vertical loads, so the addition of a vertical excitation from the earthquake is usually not very significant in the overall strength of the building. When we look at earthquakes, geologists measure earthquakes in terms of magnitude, and most of you, I'm sure, are familiar with the Richter scale, which is the most commonly reported magnitude scale, but there are other scales of measuring earthquake magnitude that are used by geologists and other professionals. Engineers, on the other hand, are more concerned with acceleration, and that's the rapid movement of the ground and thus the building. The ground accelerations vary for a given earthquake, depending on a lot of factors that we can talk about shortly. And the accelerations also vary by building period. And the building period is the time that it takes the building to sway back and forth one cycle. And shorter buildings usually have a period of less than 1 second, and taller high-rise buildings usually have periods greater than 2 seconds. So you can see from this plot on the right, it shows you the variation of accelerations on various building periods. And what this also shows you is the variations that can occur within a common earthquake. All of these squiggly lines here are different ground motion records from the same earthquake, and this is the earthquake that occurred in Christchurch, New Zealand a couple of years ago. So depending on what actual site you were at, the building could experience a different level of earthquake shaking. So some of the factors that contribute to this variability are the earthquake magnitude itself. The stronger the earthquake is, obviously, the stronger the ground shaking is going to be. But some other important contributing factors are the distance of the building from the epicenter will affect its ground motion, and also the local soils condition at the site will affect the ground shaking. And these effects will be the acceleration of the ground plus the displacement produced by the earthquake. So if you want to know what the likely effects of an earthquake would be on a specific site, you need a site-specific hazard analysis. And this analysis considers a number of different factors. First of all, the distance from the site to each fault that might be in the area. And the effect of this is what's called attenuation, because the earthquake motion will dampen out slightly from the earthquake to the actual site. So for a given site, you would need to consider all of the major earthquake faults in the area. And then each fault itself has a particular magnitude of earthquake that can be developed and a probability of occurrence of that particular major earthquake on that fault. So what seismologists do is they consider for a given site all of the potential earthquake faults and aggregate the probabilities to come up with a range of hazards that may occur at that site over time. And the result of that hazard analysis is what we call a hazard curve. And what you see here is a group of hazard curves for various sites throughout the United States. What you can see is on the left axis is the return period, and note that this is a logarithmic scale. And on the bottom, the horizontal axis, is the peak ground acceleration that's expected for the earthquakes. The horizontal colored lines represent different average return periods of earthquakes. So you can see that the length of time that you consider has a huge effect on the expected ground motion. The green line represents a 475-year earthquake, and the purple line near the bottom is the 2,475-year earthquake. So depending on what part of the country you're in, there can be a huge difference in the expected ground motion depending on what type of return period you want to consider for your seismic hazard. So up until about 2003, most building codes used in the United States assumed a seismicity based on a 10% probability of being exceeded in 50 years, which is, if you look at the previous slide, a 475-year average return period earthquake. Since about 2003, building codes have changed their definition of seismicity, have now used a seismicity which is based on what's called the maximum considered earthquake, or the MCE, and this is represented as a 2% probability of being exceeded in 50 years, or the 2,475-year return period earthquake. So there has been a huge change in how seismic hazards are defined in the United States in the last 10 or 15 years. And the reason for this is the expectation that large earthquakes on the East Coast were not properly considered with a lower probability or a lower return period earthquakes. So here is a seismic hazard map of the United States using the definitions that we've described before. And this is on a county-by-county basis throughout the United States, with the highest anticipated accelerations within the county defining what the region of seismicity is. And as you'd expect, most of California and the West Coast Oregon and Washington are very high seismic. There are a couple of pockets of high seismic areas in the New Madrid area in southeast Missouri, and then there's a little bit in the Charleston, South Carolina area, and very large sections of the Midwest and East that have very low seismicity. So when we're looking at a building or an individual structural element, we're concerned about the actual behavior of the elements. And the reason for this is, as we described before, buildings are designed to be damaged in a major earthquake. That's the expectation we do in design. And the reason we can do this is because we introduce a behavior into the structural elements that would be appropriate for being damaged. And that's what we call a ductile or nonlinear behavior, plastic behavior, which is represented by the green curve. As you push on a building that has a ductile behavior, it will reach its yield point where it starts to deform, and then it will still be able to hold its strength as it continues to deform. The red curve, on the other hand, is representative of what we call brittle behavior. It is behavior that when the structure or element reaches its yield point, it loses its strength very rapidly and is no longer holding any strength. So for buildings and elements that have good ductile behavior, we can allow them to have some damage because we know that they're still going to be standing after the earthquake. On the other hand, if we have brittle behavior, we would not be as comfortable with that, so we would not like to have that kind of behavior. So when we look at structural performance, as we just described, engineers have defined several levels of seismic performance of the structural elements that vary depending on how much damage we anticipate. So the best type of performance is what we call operational performance, and this is where the building, the structure stays completely elastic with no damage during the earthquake. The next level of performance is what we call immediate occupancy, and this is represented by the green line on the intersecting the curve. In this case, we might have a little bit of structural damage, but in most areas, the building is undamaged and continues to function following the earthquake. The most common level of performance that we use for design is what we call life safety, and this would anticipate some level of damage to the building that would not be sufficient to keep people from leaving the building after the earthquake. We would want to make sure that everybody is safe within the building. And then there's a level of performance we call collapse prevention, which is when the building is severely damaged but still standing up, sufficient that people can get out of the building following the earthquake, but the building may be trashed and may no longer be usable after the earthquake. And we have two intermediate performance levels, one between immediate occupancy and life safety, which we call damage control, which is an intermediate level, and again, an intermediate level between life safety and collapse prevention, which we call limited safety. Now, when we combine the structural performance level with the ground motion, we can do so in a matrix such as this, where we have an orange line representing what we call a typical building or a risk category 2 building. For a frequent earthquake, we'd expect immediate occupancy type of performance. If you got to a larger earthquake, which is a design level event, we'd expect life safety performance. But if it's experienced the maximum credible or capable earthquake, the MCE, we would want that building to have collapse prevention performance. On the other hand, if you had an essential facility, such as a hospital or emergency operations center, that would be a risk category 4 building, which is represented by the green line. In that case, you want operational performance for the frequently occurring earthquake. You might want immediate occupancy performance for the design level earthquake, and you would want it to continue to have life safety performance in the maximum earthquake. And the blue line in between is what we call the risk category 3 buildings, which would be high occupancy type buildings, which we might want some kind of intermediate type of performance. Now, when we talk about the performance of buildings, we're usually concerned with the structural framing, but in addition to that, we also want to consider the non-structural elements that are part of the building. And these can include several different things: the architectural components of the building, the utility systems, which would be mechanical, electrical, and telecommunications facilities, as well as the furniture and contents within the building. And here's a pictorial representation of a building showing all of these different non-structural components. The green elements would be the structural framing. The black elements would be the architectural elements, which would be visible to the occupants. The purple elements are the building utility systems, which are usually hidden by the architectural elements. And then there's the orange contents and equipment that would be within the building. So to highlight some of the typical architectural elements, they could be either on the interior or exterior of the building. On the exterior, we have things like parapets, chimneys, exterior ornamentation, as well as the curtain wall cladding and glazing systems. On the interior, we have partitions, ceilings, interior ornamentation, and other things. All of these are architectural elements which need to be attached to the building to prevent them from falling and hurting someone. The building utility systems include a large variety of things, as I mentioned before. We have HVAC equipment, plumbing systems, tanks, electrical equipment, and telecommunications equipment. These are usually heavy systems that could fall and potentially hurt somebody if they became dislodged. And finally, we have things that are non-permanent items within the building, usually tenant-supplied items that are the contents. These generally are not well attached to the structure, if at all. And some of the more typical things that can cause problems would be shelving and other things that are on display or portable pieces of equipment. So similar to when we talked about structural performance levels, we have various levels of performance for non-structural components. Again, operational being the best performance, in which these non-structural components can continue to operate during the earthquake. And then the next level of performance is what we call position retention. In this case, we want the items to stay in place during the earthquake, not fall down and hurt anybody. But in position retention, we're not guaranteeing that those pieces of equipment may necessarily function following the earthquake. For life safety, it's basically a subset of non-structural components that are critical to affecting the safety of the occupants. Things that would fall and typically hurt somebody in an earthquake, those things are restrained. Other items may not be necessarily restrained. And then there's a level where the non-structural components are not even considered or braced for earthquakes. So when you combine the building performance with to define the building performance, we have a given earthquake shaking, and that will result in a performance level for the structural framing and a non-structural performance, and those two combined define the building performance. And the building performance affects three different aspects. One would be the safety of the occupants. The second would be the amount of cost required to repair that damage following an earthquake. And then finally, how immediately you could occupy and recover and continue to use that building following an earthquake. So I'm going to turn this over now to Kelly to talk to you about characterizing types of buildings.
Thank you very much, Brian. If you talk to an engineer about the likely earthquake performance of a particular building, chances are very high that that engineer would start talking to you about the type of building and characterizing the building. They might be talking about the materials of construction, about what the earthquake resisting system is, about the age of the building. And for example, the building you see on the right-hand side here is of multi-story wood frame construction. It has an earthquake resisting system that's likely shear walls. And this one is in 1920s era original construction. So why is it that the engineer would tend towards these things to talk about them? Well, these characteristics and these building types tell us a lot about what the design and construction might have been at the time the building was originally constructed. They tell us a lot about what might be vulnerabilities that have shown up in previous earthquakes that could potentially show up in your building. They can relate to key code changes where there was a change that might affect the expected performance of a system before and after the code change. Altogether, they give us a good idea of what the general performance of the building might be. And most importantly, because they give us a good initial idea about the performance, they are used in the evaluation methods for seismic evaluation that Brian will be talking about shortly. Now, there are some limitations to this. Not all buildings will easily be characterized as a particular common building type. In some cases, like the photograph on the right, a building might actually have several different building types encompassed in it. This particular one has wood frame construction on top and concrete construction below. Some buildings, on the other hand, just don't adequately fit into any building type and shouldn't be fit in if they don't. The other thing to keep in mind in terms of limitations is that this is a first step in understanding the building. It isn't the final step. You can learn a lot from it, but there are still a lot of details about the construction that can help fill out the picture. What I'd like to do is to introduce a few of the common building types. And first up, we have wood construction that actually comprises a tremendous amount of our building stock out there. The categories that the evaluation methodologies have under wood construction include wood light frame, single-story, multi-story, particularly smaller buildings, multi-story wood frame getting into larger buildings, and commercial and industrial, and those pretty much cover the single-family, multi-family residential seen here, as well as on the left-hand side, the commercial buildings. Another very common building type is steel, and there are a wide variety of systems that might fall under steel buildings. Steel moment frame, steel brace frame, light steel frame, dual systems, steel frame with unreinforced masonry infill, steel plate shear walls. What you see in the photograph on the right side here is a steel braced frame. And one thing to note here is that for the most part, the steel structure is covered by other cladding elements. And so you would commonly go to building plans or places that the structure is exposed in order to confirm that the building is in fact steel frame. Another very common building type we have in our building stock is concrete. On the lower left, you see a concrete moment frame building. And in fact, this particular building has a very nice expression of the horizontal beams and the vertical columns that are not only the exterior of the building, but both the gravity and the earthquake resisting system. On the lower right, you see a concrete shear wall building. And on the upper right, you see a concrete moment frame that has unreinforced masonry infill. Precast concrete is also fairly common in our building stock. The two photos that you see here are tilt-up construction, where the walls are cast on site and then tilted up into their final location. Also within this building type are precast concrete frames that are generally cast in a fabrication yard and then erected on site. Another building type that is well represented in our building stock is masonry. And the categories included in the evaluation methodologies are reinforced masonry, both with flexible diaphragm or floor and roof systems, and this might be wood-framed floor and roof systems, or stiff floor and roof systems such as concrete. Also very common, particularly in the older parts and older downtown parts in our building stock, are unreinforced masonry buildings like the one that you see on the lower right-hand side. So now we're going to talk about common vulnerabilities, and one of the things I mentioned was understanding the building type can do a lot to help us understand what vulnerabilities we might see in the buildings. And so I'm going to go through a few fairly common vulnerabilities. Some of them will apply only to a single building type. Some of them apply to several building types. And then there are a few that can go broadly across all of the different building types that we might be looking at. The first one that you see here is referred to as non-ductile detailing. If you look on the right-hand side, you'll see the concrete moment frame building that we were looking at earlier with the nice expression of the horizontal beams and vertical columns, and a red square that shows the base of one of the columns. On the left-hand side, you see the result of non-ductile detailing that might characterize a frame building built to an older code where there isn't enough horizontal hoop reinforcing in order to get good performance of it. And so this is non-ductile detailing. And if you hear the buzzword non-ductile concrete, this would be one of the potential vulnerabilities or behaviors that fall into the non-ductile concrete category. The second one, again, looking at our concrete moment frame building, but this time if you look on the right-hand side, we're looking at what might be behavior at a beam to column joint. The newer codes have in place detailing requirements and proportioning requirements that try to favor any damage that is going to occurring in the beam as opposed to the column, because the hazards presented by damage to a beam are much less than the hazards potentially with the damage to the column. If you look on the left-hand side, you see a frame to an older code that was not detailed for that requirement, and in fact the beam above is substantially intact, while there has been very substantial damage to the column. One additional vulnerability to look at for the concrete moment frame buildings, and if you look on the left-hand side, you will see a parking structure type of building, and this is in fact the same type of system, or intended to be the same type of system as we saw on the two previous vulnerabilities, where it is a concrete moment frame. And if you look at the red lines introduced over the photograph, they show the same horizontal beam and vertical column frame that is supposed to, as Brian explained, behave ductily in the earthquake and be able to move a wall while retaining strength. Now, in this particular case, the construction of a perimeter half-height wall actually restricted the ability of that frame to move the way that it was structurally intended to, and turned a ductile moment frame system into a brittle short column system. And if you look on the right-hand side, a little bit fuzzy, but I think you can see it, the top column that you see there is pretty much completely cracked through and deteriorated. On the bottom there did in fact used to be a column there that has been turned into a pile of rubble, and you can see on the left-hand photo that in fact that second floor has dropped down for a fairly substantial collapse for this building. One of the vulnerabilities that can apply to several different building types is the soft or weak story. On the left-hand side, you see a concrete moment frame building with masonry infill that had a ground floor that was not strong enough and in fact has collapsed. On the right-hand side, you see exactly the same behavior for a wood frame building. And another vulnerability that is, again, applicable to multiple building types is wall anchorage. If you don't have adequate anchorage of the wall onto the structure, you can lose portions or all of the wall, and you can then lose the roof or floor that that wall is supporting. On the left-hand side, you see an unreinforced masonry building that has lost the wall and has a in-progress collapse of the roof structure above. On the right-hand side, you see the beginning of the same behavior in a concrete tilt-up building, where the concrete panel is starting to tilt away from the roof. It's lost the wall-to-roof connection, and it's only because they were able to get temporary bracing in that panel has not fallen off. Brian mentioned non-structural elements and hazards created by them, and they also can occur over a wide variety of building types. This particular one is a parapet collapse. If you look across the top of the building, you'll notice that there is quite a bit of the parapet missing, and if you look down at the ground level, you'll see that the bricks that used to be up at the top are now at the ground. This obviously, while non-structural, can be fairly severe damage and a fairly severe hazard created by that damage. I mentioned that there are some vulnerabilities that occur across all building types, and one of those is a geotechnical hazard. This particular building had a failure of the soil underneath the building during the earthquake that really caused collapse of the building. In this case, it rolled over, but it could equally have deteriorated into a pile like the building you see in this final photo here. So adjacency hazard is a final vulnerability that I will introduce. And what you see here in the middle is a building that appears to have gone through the earthquake without any substantial damage. However, because of the very substantial damage and really collapse of the neighboring building, the building in the middle is not usable and may in fact be damaged by that neighboring building. So it can extend beyond just your building to the building next door. And this is a behavior that we saw following both the Christchurch and Napa earthquake, and it is one of concern and worth consideration. I will now turn it back over to Brian to talk about evaluation methodologies.
All right, thanks, Kelly. So given that background, we have at least some basic tools for doing some evaluation of buildings, and with the understanding of the need to characterize building types and to be looking at these common vulnerabilities. And so these basic techniques have been used to define a number of different methodologies, and the methodologies for doing seismic evaluation can vary dramatically from a very simple type of evaluation methodology to much more complex. And what we're going to be talking about today is three basic types of methodologies, one called the rapid visual screening, another one which is defined by the ASCE document, seismic evaluation of existing buildings, and then further updated into seismic evaluation and retrofit of existing buildings, which is a three-tier process that we'll be describing. And then the International Existing Building Code has a number of chapters in its appendix which talk about various types of methodologies for looking at common building types. So first, if we want to look at the simplest type of evaluation methodology, it's called the rapid visual screening. This was first introduced in about 1988. It's been updated a couple of times. The most recent edition, which was just published 2 months ago in September of 2014. The purpose of this is to evaluate the seismic safety for a large inventory of buildings quickly and inexpensively with minimal access to the interior of the building. So if you have a large portfolio of buildings that you want looked at, to do a screening to figure out which buildings are hazardous and which ones are not, this would be a very useful first step. So the way this procedure works is what's called a sidewalk survey, just visual observation from the outside of the building, usually taking 15 to 30 minutes, depending on the building. Access to the interior of the building is optional. It's not required for part of this evaluation. The first step would be to determine what seismic hazard is associated with that building type, and that's based on the information provided by the U.S. Geological Survey. Then, as Kelly mentioned, you want to identify the model or the common building type associated with the building, and each common building type is then assigned a basic score. The next thing would be to look for those vulnerabilities or the important characteristics that might affect its performance, and those provide a score modifier. You add up the basic score and the score modifiers. Score modifiers are usually negative numbers to subtract, indicating vulnerabilities, and you come up with a final score for the building. And if your building score is less than a predefined cutoff score, the building then needs to have a more detailed evaluation. A higher score indicates that no additional evaluation is needed. So in addition, in the latest version of this rapid visual screening, we have a two-level process. The second level would be optional, but the first level would be a single-page form that's filled out. And this could be filled out by anyone with a very good background in building construction. It could be an engineer, architect, other design professional, or a contractor or student. Anybody that's been properly trained can figure out how to do this initial screening. There is an option for this level 2, which is another level or another page of form that can be completed. This requires a little bit more rigorous assessment of the building structure and the non-structural components with very little additional effort that might be required on the part of the screener. But this needs to be completed by a qualified design professional, an engineer preferably, that has experience in seismic design to make sure that this part of the evaluation is completed properly. So some of the advantages of using a rapid visual screening is that it can be completed in a very short time, and you don't have to have a lot of previous knowledge about the building. The form can also be done by somebody with very basic knowledge of seismic design. You don't have to have a lot of experience for that. And it's very useful when you're talking again about large inventories of buildings if you want to prioritize your further evaluations or retrofits. And these types of screenings can usually identify many of the critical vulnerabilities that Kelly discussed. But some of the limitations in trying to use this procedure is you may not actually be able to determine what the building type is because you're only looking at it for such a short time. And as Kelly described, a lot of the structural elements may be covered by finishes. So to accurately define the building type is sometimes very difficult. And this is also not applicable if you're looking at a building that doesn't fall into one of the common building types that Kelly described. This rapid visual screening considers some non-structural hazards, but not all of them because you're not going in the building and you're not looking at a lot of the interior non-structural hazards. So the non-structural hazard evaluation is very limited. And buildings that don't pass this screening require some additional evaluation in order to figure out what the real hazards and what would be needed to fix them are. The next level of evaluation in terms of complexity is what's called the Tier 1 screening, and this is defined in two different documents. The ASCE 4113 is the more modern document, which supersedes the ASCE 31. And the intent of this screening procedure is to identify buildings that require some additional evaluation. The buildings are evaluated looking for common structural deficiencies by building type as we described before, but it's looking at it in a lot more detail than you would with a rapid visual screening. But this is still a very rudimentary evaluation procedure. So we're not looking at every deficiency that might exist. It's not a thorough design evaluation of the building, so there could be some deficiencies that occur in the building that would not be identified by this Tier 1 screening. This methodology is intended to be very conservative and may actually flag buildings that are good as potentially hazardous. So it's important to realize that buildings identified as not passing Tier 1 are not necessarily bad. It just means that they need further evaluation. Some of the other limitations to this screening are there are height and building type limitations. The height limitations will vary depending on what level of seismicity you're at, with buildings in high seismic areas having lower height limits for applicability. Very tall or unusual building types will require a more systematic evaluation than can be done in the Tier 1 screening. And this is also applicable only if you're looking at two levels of performance, life safety, or immediate occupancy. So the basic procedure is to go through a checklist or a series of checklists, which can be either which will vary depending on the building type. There is a basic configuration checklist which would be applicable to any building type, and then there's other checklists that are specific to individual building types. And these checklists will vary depending on the performance level, whether you're looking at the life safety or immediate occupancy performance level. And the actual questions that you have to answer in the checklist will vary depending on the level of seismicity that you're looking at for your specific building. So the basic configuration checklist as shown on the left would be some of the vulnerabilities that Kelly discussed: soft and weak stories, adjacent buildings, foundation, and geotechnical conditions. Some of these evaluation are going to be quantitative evaluation, where you need to define what your seismic force demands are on the building, determine material strengths, and then compare the strength to the demand. Other aspects of the evaluation will be more qualitative, which will require a review of construction details from the original drawings, if those are available, and some site observations of the existing building conditions. In addition to looking at the structural components, the Tier 1 procedure also has a requirement to look at some of the non-structural components. And this requires a qualitative assessment of the non-structural components and its attachments. For life safety performance, in this type of evaluation, we're only looking for credible threats to life safety, things that have historically in the past caused serious injury to people. There is a second level performance called position retention performance. In this case, we would be looking for the non-structural components to stay in place, but would not necessarily be operational during or after the earthquake. Now the ASE 41 also has a Tier 2, which is a more detailed evaluation methodology, and this is what's called a deficiency-based approach, in which case any deficiency potentially identified in the Tier 1 evaluation would require some more detailed analysis. This detailed analysis may require a full building evaluation, or it may be a localized evaluation of a specific part of the building. In many cases, the analysis is going to require some computer modeling of the building in order to do that evaluation. And finally, we have the more sophisticated or evaluation, which is called the Tier 3 systematic evaluation, and this would be applicable to any building type. It accounts for the actual structural behavior of all of the critical structural elements within the building, and it considers not only their elastic behavior, but their behavior beyond the initial damage or yielding of that structural element. Material testing to determine the actual properties of those elements is encouraged to greatly improve the accuracy of the results. And you can look at multiple levels of performance using this type of approach in contrast to the other types of performance. The main disadvantage to doing this systematic evaluation is very, very time intensive. It requires lots of detailed computer modeling. a thorough understanding of all the building components, their configurations, and their structural properties. And in doing so, doing this systematic evaluation doesn't necessarily mean that the building's going to give you any better results. You're not going to necessarily get better results using a more sophisticated analysis. In some cases you will, but in other cases more analysis may not do you much good. So this systematic analysis is going to require usually a computer model considering all the significant components of the building. Detailed properties are going to be needed to be input, and you're going to usually look at demands that are site-specific for the building, and you have to usually consider multiple seismic demands, multiple types of earthquakes, a lower level potentially of earthquake and a more extreme earthquake. And then for each earthquake that you're looking at, you want to compare the component's demands to its capacities, and the capacities will, your allowable capacities would vary depending on what level of performance that you're looking at. So in addition to these evaluation methodologies, the International Existing Building Code has an appendix that has some chapters in it to discuss specific building types and the evaluation methodologies that might be appropriate for those building types. One of the more common types of these evaluations is for unreinforced masonry bearing wall buildings, which is described in Chapter A2. But there's other chapters in the IEBC looking at reinforced concrete buildings with flexible diaphragms, wood frame buildings with cripple walls, wood frame buildings with open or weak storefronts, and concrete building, older concrete buildings. So these are other evaluation methodologies that can be used if you know what building type you have. So when you want to do an evaluation of the of an existing building, there's important considerations as to when you would want to do this. One common type of evaluation is triggered by the building code, and this is normally going to occur if you have additions, modifications, or a change in occupancy of the building that would trigger a seismic evaluation of the building. There are some conditions where the local jurisdiction would have some mandatory evaluations. This might be for conditions identified as unreinforced masonry or a soft story wood frame structure are two common types of buildings that require an evaluation. Evaluations may also be required by the money lender for the building, an insurance company, or a requirement for, by the tenant of the building. This is usually, if it's government leased building, there's a requirement for a seismic evaluation. And of course, there is also the owner's discretion to voluntarily do an evaluation of the building to determine its vulnerability. So when you're evaluating the building, some of the important considerations are, one is to choose an engineer to do this evaluation, recognizing that engineers are not necessarily a commodity, that seismic experience is very critical to getting a good evaluation and a proper evaluation for the building. Having good information on the construction of the building is critical to getting a good evaluation. Incomplete information about the building leads to a lot of uncertainty. So the more information regarding the construction of the building that's available to the engineer, the better the evaluation is going to be in terms of accuracy. And when choosing an evaluation, you need to discuss with the engineer what the needs and expectations are for the evaluation and for the expected building performance prior to any type of evaluation. Some of the issues that you need to also consider are that there are engineering limitations. As I said, there's a lot of uncertainties in the evaluations, and those uncertainties are going to be reflected in the results by the engineer. There's also other things about the building that the engineer may not have any control or knowledge of, which may affect the not only the evaluation but the decisions regarding the building. Things like the repair costs and time cannot necessarily be predicted ahead of time to know what kind of costs or downtime might be expected for a building that might be damaged. You also don't know what might be required in a post-earthquake environment, whether the building might have to be upgraded or could be just put back the way it was following an earthquake. And there's also external factors outside of the building that will affect its performance and functionality, things like transportation to and from the building and the impact of utilities that service the building all affect the seismic evaluation and the expected performance. In doing any type of seismic evaluation, you always have to consider the costs of doing not only the evaluation but the retrofit itself and what the expected benefits would be. You don't want to, there's limited availability of funds for any type of this evaluation, so you want to look at which buildings are going to get you the most benefit for spending your money for evaluation, and you may end up looking to do other ways of dealing with buildings that might be vulnerable. And also, finally, the use of the buildings may have some limitations on how you go about doing the evaluations. Buildings that are in use 24/7 obviously may have more critical uses and may thus be prioritized more heavily in terms of evaluation needs. And finally, let's talk a little bit about seismic retrofitting when that is determined to be needed based on the evaluation. In looking at an evaluation, you need to allow for uncertainties. There are going to be hidden conditions that you run into in a seismic retrofit that would not be anticipated. So the expectation of knowing that uncertainties and hidden conditions will exist is something that you need to plan for in advance. In a lot of cases, you may want to consider incremental implementation. This may minimize the amount of disruption that you have for the building. If it's a building that has to be occupied during the work, which is normal, and the incremental implementation can also help spread the costs out over time. And it's all important for the building owners to understand that there's going to be multiple consultants that they have to manage during the whole process. You've got the engineer, the architect, the contractor, construction manager, and probably some other professionals involved during the process, and coordination of all of these consultants is going to be critical to a good retrofit outcome. So that's the extent of our presentation for today, and Kelly and I are both open to any questions that you may have.
Now let's see if we have any questions. Okay, we have one here. It says, I thought that building codes produce buildings that would not be damaged by earthquakes. When did the building code change to accept that buildings could be damaged in an earthquake?
Well, the answer is that building codes have always had that expectation. It was only about 15 or 20 years ago where engineers actually started communicating that information to their clients in writing, but it's always been the expectation of damage that would happen in an earthquake, but engineers were not very good previously at letting their clients know that.
All right, thank you, Brian. I have another question here. How can I, as a layperson, evaluate engineers for a study?
Well, I think the most important thing is to get some qualifications from the engineer regarding their experience in doing evaluations, what type of professional background they have. It's very important for evaluating buildings that the engineer has actually done that type of work, and they're not an engineer that focuses mainly on designing new buildings, because dealing with existing buildings can be very different.
It's also a good idea to interview or talk with the engineer and make sure that they are someone that is going to listen to and understand what your needs are and be able to turn around and present you options that are responsive to your needs.
Okay, we have another question. Can you talk about PML, SEL, SUL calculations and how those relate to the assessment methodologies that we discussed today?
Well, they don't. In short, the methodologies used to create PMLs, SELs, SULs, etc. And for those that aren't familiar, PML stands for probable maximum loss. SEL stands for scenario expected loss, and SUL is scenario upper bound loss. These are numbers that are produced by, supposedly by an evaluation to indicate what the cost, relative cost of damage would be to the value of the building. And there is no standard methodology that's provided for the analysis to come up with those numbers. It's really up to the engineer to decide how they want to come up with these PML and SEL numbers. The only standards are in terms of defining what the hazards are that you must use to determine the PML and SEL numbers, but there's no standard methodology on how you would actually go about evaluating the building.
And compared to the methodologies that were presented today, the methodologies presented are published, widely used documents that have gone through various standards processes with wide community input and have a whole lot more clarity about the process, and through that clarity should lead to a whole lot more consistency in results of the evaluation.
Okay, Brian and Kelly, another question. An early slide referenced that the vertical component of ground motion is approximately 1/3 the horizontal component. How is the vertical component accounted for?
I don't think it's referenced 1/3. Normally what's considered is the vertical is 2/3. And the way it's considered is, well, there's two ways. There is some requirements for a reduction. When you're considering the effects of gravity load and earthquake at the same time, you would reduce the benefit of the gravity load that may be resisting the earthquake. That's one way of accounting for the fact that the vertical earthquake may be acting in an opposite direction. More typically, the effects are considered are just ignored because it's really not that important. Based on studies that have been done, the amount of earthquake shaking in the vertical direction is usually very small and does not affect structural components. But there are some very limited cases where it is explicitly required to be considered, but that's usually for very limited types of elements.
Okay, we have time for one more question. Can you speak in any general terms about the strengths and weaknesses of mid-century moment-framed high-rise, 25 to 30 stories, high-rise buildings?
That was mid-century, you said?
Yes.
Well, I think a lot of it depends on the type of structural system that's used for those buildings. If it's and the use, if it's a commercial building, it's most likely to be a steel frame, steel brace frame, or a concrete shear wall type of building if it's mid-rise. And those can have a wide variety of performance depending on the building type. So it's very difficult to characterize the performance of those buildings without knowing more specific about what the actual building type is.
One important thing to think about, though, is whether it's a concrete or a steel building, there have been a number of fairly significant changes in approach to design of those buildings and retrofit of those buildings over the last half century. And so it is worthwhile to take a look at that type of a building to figure out if there have been changes in thinking that are significant to the performance and what it implies for the performance of that particular building.
All right, so thank you very much for everyone who attended, and thank you, Brian and Kelly.